All right, so here is another calculus lecture. So where we left off last time was that we were finishing off a lot of things related to limits and differentiation. And so now we're going to move into concepts about anti-differentiation and reminding everyone some of the fundamental definitions related to this and also some of the practical stuff, just like we usually do. Some of the practical things that you need just to take your day-to-day integrals and stuff, but then also understanding why these things are true. So here is a good statement, again, taking everything from Stewart. So find a function f whose derivative is a known function little f. If such an f exists, it is called an antiderivative of f. So the antiderivative is going to be when you find some function where when you take its derivative, you get this function f. And so the antiderivative is whatever it is where its derivative equals f. And so the definition then of an antiderivative is that a function f is called an antiderivative of f on an interval I if f prime of x equals f of x for all x in I. That's just a definition. So for example, say we take f of x is equal to x squared, then an example of one antiderivative of this is f equals 1/3 x cubed, because you take the derivative of this, you get back the x squared. But then another one is g of x is equal to 1/3 x cubed plus 100. Or in general, h of x equals 1/3 x cubed plus c for a constant c. These are all antiderivatives of f, so the antiderivatives are not unique. And so you'll also notice that these seem to have a lot of relationship to the things we've been doing with differential equations, and when we have like a general solution versus a particular solution and we get these constants. So then a viable question is, okay, so it looks like there's lots of antiderivatives. So I could write them like this, but are there more of them that I'm not thinking of? So you can actually prove that that this is like, no, you've got them there, because it turns out that you can prove that if two functions have identical derivatives on an interval, they differ by a constant. You can write this mathematically as that if f prime of x is equal to g prime of x for all x in an interval AB, then f minus g is constant on AB, or that f of x is equal to g of x plus c for some constant c. So this has a lot of relevance then to when we do our integration as part of solving differential equations and we get our integration constants. This is helping us know that as we're doing anti-differentiation essentially, and we're saying the derivative of whatever function is equal to the right-hand side of the differential equation. The derivative of that is equal to the right-hand side. What function could possibly give me that? And then this tells us that like the set of functions that could, for example, be the antiderivative of f of x equals x squared, that we would be able to capture them in some other function. Was ist constants? So, next thing is that the most general antiderivative of a function f on an interval I is some antiderivative plus c, where c is an arbitrary constant. So let's define sigma notation. So here we have that the sum from I equals 1 to n of f of xi delta x. What this means, again, for anyone who may have forgotten, you put the part where there's the I, you plug it in, then you make the sum. So the next one plus dot 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 all the way up until the upper side of the sum. Okay, so now let's remind people of what the actual definition of a definite integral is. So if it's been a while, let's go to fundamental definitions like we like doing. So the definition of a definite integral is that, so again, I'm going to take this from Stewart and I'm going to just do word by word. So if f is a continuous function defined for a is less than or equal to x is less than or equal to b, we divide the interval AB into n subintervals of equal width. Delta x equals b minus a over x. Or sorry, n. Sorry. We let x equals, or x0 equals a. So it's going to be this left-hand side of the interval. And we have x1, x2, dot, 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 to xn, where that's going to equal the other side. Be the endpoints of the subintervals. And let x1 star, x2 star, dot, 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 xn star be any sample points in the subintervals. So xi star lies in the I subinterval. X I minus 1 comma xi. So then the definite integral of f from a to b is the integral from a to b of f of x, of x dx is equal to the limit. This is really making a lot of straight marks right now. The limit as n goes to infinity of the sum from I equals 1 to n of f of xi star delta x. So a few points. This is what we call the integrand. These are the limits of integration. Dx is not this goes like dx has a symbol for that. You can see how it kind of the symbol almost makes sense in the definitions, but this is definition. This is the symbol used for this. So that's really important to remember. So we said there's a limit definition of this. There's also this limit definition for integrals. And also remember that the integral gives you a number. So in this case, it's not going to depend on x, it's going to be a number. Okay. What does this kind of mean then in some type of precise notation? Because it can be demonstrated that it doesn't matter like which point you take in the interval. So then what would this probably mean in some type of more precise notation if I was trying to understand what is being said here? And so say that what it ends up being is that essentially for every epsilon greater than O, there exists an integer n such that the excuse me, the integral from a to b of f of x dx minus this other thing, which is what it's equal to in the limit, is less than epsilon for every integer n and for every choice of xi star in xi minus 1 and xi. So oh, sorry, I forgot a part here. For every integer n greater than n. Sorry for that. So yeah, so for epsilon greater than 0, there exists an integer n such that as long as this n is sufficiently large, then I'm able to get this value of the sum to be arbitrarily close to what the value of this integral is. And so we essentially what this means. So here's the definition of integral, and then we can try to figure out what does this mean here. It means that when I make a lot of as I make the n bigger and bigger and bigger, I'm able to always find an n, so that if I make the greater than a given number, then no matter what way I choose these sample points in the intervals, I'm still able to get the integral minus this other term to be less than epsilon, and then that would indicate to me the value of the integral. Okay. So then this also should hopefully remind people some cool stuff, because then when we actually evaluate an integral, oh my goodness, evaluating integrals. So the interesting part is that just like in the last lecture that we went through and we said, you know, if derivatives are defined in terms of sums, everything, or sorry, in terms of limits, then everything that I know about the way that the derivatives like rules are, like product rules, quotient rules, sums and linearity, also things about like that the derivative of certain things is other things, all of that actually comes then from applying the fundamental definition of limits, and that you can prove that each of those things is true from those. And so we can also prove that a lot of the things that we take for granted with integrals also come from the fundamental definition of a integral as being the limit of a sum. And so I can demonstrate this for a few examples so that people can see what an integral really is, because it's always very helpful to see it not just in notational form, but in like, what does it mean to actually do an integral? But to have these, there are like a few things that people need to know about some sums. So I forget which ones of these I actually use. I should have written that down, but I just copied all of the ones out of the book for the things that were true about sums. So sorry for this minute while I'm probably writing stuff out here that may not be used in a second. But it's possible to calculate all of these. Oh, sorry, to n up here, and this is c. Equals nc. Sum from I equals 1 to n cai. C. Sum from I equals 1 to n ai. Sum from I equals 1 to n of ai plus bi. Equals the sum I equals 1 to n of ai plus the sum equals 1 to n of bi. And then finally, this last one is the last one I wrote down that's true about sums. It's equal to the sum from I equals 1 to n ai minus the sum from I equals 1 to n bi. So if anyone wanted to prove any of these, they could, of course, actually like write out these sums and demonstrate that these things were true. But now let's look at an example of actually doing a limit. So the limit version of this integral. So here's what we got. And so from the definition of the interval, or of the integral, we are going to divide our range from 0 to 3 into n subintervals of equal width, delta x equals 3 over n. And then, so then we could go from there and say like, okay, I'm going to put the first endpoint at 0. And I'm going to put the endpoint of this interval on the right-hand side at 3 over n. And then I'm going to have another endpoint of an interval at 6 over n, and so forth. And so we can see a pattern developing here. We can see that every xi is equal to 3i over n. So this is for I is 0, it becomes 0. I is 1, we multiply 3 times 1 over n, and it's 3 over n, and so forth. And so because we said that you can prove that you can use any choice of xi star in the interval works out, which I didn't show how to prove this, but I'm just stating that it can be proven. Let's take the right endpoints, because why not? So if we do this, then by the definition of the integral, here's what the symbol means. It means that whatever this number is equal to the limit as n goes to infinity of this sum from I equals 1 to n of xi star cubed minus 6xi star times delta x. And then we said, okay, I'm going to choose our xi star to be the right endpoints. So it's going to be like 3n, 6n, et cetera, all the way up to 3n over n, so up to 3. So this is going to be equal to the limit as n goes to infinity of the sum from I equals 1 to n of, and so now we have to plug in the endpoints. And so like we just said here, this is really the right endpoints of every interval. So we have 3i over n cubed minus 6 times 3i over n times my delta x, which I have here, which is 3 over n. And then we can do some simplification mathematically here. And what you would get if you like multiply 3 to the third, so that's 27 times another 3, so 81, and then same thing 6 times 3 times 3. And then taking out anything that involves n, because this sum is over I, not over n. So then we would get like 81 over n to the fourth. Sum from I equals 1 to n of I cubed minus 54 over n squared, sum from I equals 1 to n of I. And so now we can use this one here of I cubed and this one here. So in that case, we will be able to plug those in. And so then this is going to be a limit as n goes to infinity of 81 over n to the fourth times, then we plug in one of those two definitions that we had, so n times n plus 1 over 2 squared minus 54 over n squared times this other sum, which is according to the example page, times n plus 1 over 2. And then we can eventually keep going here until we get the limit as n goes to infinity of 81 over 4 times n squared plus 2n plus 1 over x squared minus 27 times n plus 1 over n. But then, oh, sorry, I put the bracket in the wrong place. Okay. But then the interesting thing at this point is in the last lecture, we were interested in limits as our number that we were saying the limit as something goes to infinity. And so in this case, we have that. And so then we have to take into account the things that we did before. And so one of the things we did before was we said we're doing these infinite limits, and there's some numbers in the top and numbers in the bottom. It's often very helpful to divide by the highest power of the thing that's going to infinity in the numerator and the denominator. So if we do that, what we end up with on the next page is I can say this equals the limit as n goes to infinity of 81 over 4 times 1 plus 2 over n plus 1 over n squared minus 27 n plus 1 over n. And then we're able to say that it's equal to 81 over 4 minus 27 equals negative 27 over 4. So it's equal to negative 6.75. So this limit definition, we were actually able to get the value of the integral. And so there's some other just stuff to remember type things. So the integral from b to a of f of x dx is equal to the negative of the integral from a to b of f of x dx. You might say, why is that true? Well, it's because then when we take the delta of x is b minus a over n, then if you flip this so that it's actually like a minus b over n or something like this, like one of that's going to be negative and one that's going to be positive, so the integrals will just be the same sum, but with like delta x being either negative or positive. So in this case, I'll flip this side. Okay, then we have that if a is equal to b, the delta x is 0, which gives us that the integral from a to a of fx also has to be equal to 0. So you can see all of this following from the definitions, and not just because I defined this symbol, but because this actually follows from a definition of what an integral is. So here, if we assume f and g are continuous, Then something that are true. So one is the integral from a to b of c dx equals c times minus a for any constant c. We also have that the integral from a to b of x plus x dx is equal to the integral of a to b of fx dx plus the integral from a to b of g of x dx. We can also take the integral from a to b of c of x dx is equal to c integral from a to b of x dx for constant c. And then we have a similar one with like also for minus. And then the other important one is from a to c of x dx plus the integral from c to b of fx dx is equal to the integral from a to b of fx dx. So there you can see some of the important properties, and then I guess those would follow from the literature. You also know some other types of things, and they're right here usually more useful for proofs, so it's good just to make sure you thought about these before. So if fx is greater than or equal to 0 for a less than or equal to x less than or equal to b, then this integral from a to b of fx dx is also positive. If fx is greater than or equal to g of x, or a less than or equal to x less than or equal to b, then this integral from a to b of dx is greater than or equal to the integral from a to b of g of x dx. And then if m is less than or equal to fx less than or equal to m for a less than or equal to x less than or equal to b, then we have that m times b minus a is less than or equal to the integral of a to b of fx dx is less than or equal to m times b minus a. So at this point we get to the fundamental theorem of calculus, which relates differentiation and integration. So the book that I was looking at, Stewart book, it calls it part 1 and part 2, and then the end, right? You can find myself. I'll write part 1. So this is the fundamental theorem of calculus. Part 1. So because that's what we called it. So it says if f is continuous on a b, then the function g defined by g of x is equal to the integral from a to x f of t dt, a less than or equal to x less than or equal to b, is continuous on a b and differentiable on a b, and g prime of x is equal to fx. So what this means, if you want to write it shorthand style, so the derivative of this from dt, which remember is just a symbol representing the derivative here, and we're saying if we also did the derivative of this sort of function of x that you're getting when you say, okay, my upper bound is x, so as I vary this x, I also get different values of this integral, and so this will be a function x, and it says that indeed this derivative of this integral is actually fx, where when f is continuous. So let's try to do a really quick example. I want to make sure I say on the slide is where this is written because I think it helps see it. So if you take the derivative from 1 to x to the fourth of secant t tangent or secant t dt, then you're going to have to use the chain rule here because this only says what happens if the upper limit is actually x, not just if it's like a function of x. And so if we do the derivative here with respect to x from, or sorry, I'm going to change every variable. I'm going to change every x to be u to represent. I'm going to take the derivative with respect to u, and then I'm going to call this x to the fourth equals u. I'm going to say u equals x to the fourth. So I'm going to go from 1 to u of d over dx from 1 to u d t dt. So far I only changed this part. I just said 1 to this variable u, 1 to this. And then we say like, okay, well ultimately I want to get the derivative with respect to x of this function, but this function is a function of u because like when it's u with a fixed then this integral will evaluate to a number, not to a function. But it evaluates to a series of numbers because this u is varying. So that means is that this integral is actually a function of u because as I change the u, I get different answers. And so I can think of this whole thing over here as being a function of u. So I'm taking the derivative with respect to a function of u, the u is equal to x squared. So this is one of those compositions that we talked about before. So this is actually d over du, the integral of 1 to u, secant t dt. Sorry, the wrong thing. I'm just replacing x. I'm doing what I just described. I'm doing the chain rule thing times du over dx. And then so then I would be able to say, oh, okay, so the derivative of this is then going to be secant of u by following this. So it's going to be secant of u and then I solve by dx. So this is going to then be if I take u and I plug it in here and then I raise to u, well, x to the fourth will be secant of x to the fourth and 4x cubed. Here we go. So then that's my final lecture. So what's the other part of the fundamental theorem of calculus? So this is part 2. So this is going to be if f is continuous, then this integral f of x dx, which is defined as a limit for subintervals going to infinity of a sum. This is going to be able to minus of b minus f of a, where f is any antiderivative of, or that means that f we started off with f. So interesting result here because what this means is that if I know some antiderivative of f, not even I don't have to know like all of them, I just have to know one of them, then that really easy that limit that we saw earlier is going to be this value. And so there we go.